So right now, at least, the iPad and the PC decided to talk, so hopefully everything works out. So amino acids are just, and once again, a lot of this was made in an older PowerPoint, so it's going to be backwards, starting at the bottom. And working this way up. But amino acids are really, really simple. They all have the same generalized backbone. And you have to know the backbone. The only exception, there's one where the R chain, I'll show you what I mean by that in a moment, where the R chain of it doubles back and connects back to itself, and that's proline. But the vast majority, all of them, you can know just a generalized backbone. You have what's called the C alpha. Whoops. I can't see that. I don't know if you can or not, but let me change the color. We have the C alpha. And if it's an amino acid, what do you suppose an amino means? It's an amino group, right? That's why. And so I'm going to hang this nitrogen off here. I'm going to show it in its ionized form, possibly. Then the acid portion of an amino acid is a carboxylic acid. Hang off of that. So we have carboxylic acid. Actually, the other program, it doesn't record videos as well, but it's easy to draw on. Okay, now, right now, by the way, I've drawn glycine. That would be glycine, because the R group for glycine is a hydrogen. But all of the other amino acids have something else. There's always a hydrogen hanging off the C alpha and then an R group. Okay. So right down here below we have what they call the, it looks like unionized, but it's unionized form versus the Zwitter ion. If you think back to Gen Chem 1, the Zwitter ion is something that's both negatively charged and positively charged within the same ion. Okay, and so it gives them some special properties. And so that's all that amino acid really is. All right. All right, these are all called alpha amino acids. That's because the C alpha has both the amino group and it has the carboxylic acid group. They're not the only amino acids out there. As I've mentioned some before, there are other amino acids out there. There are some that are called beta amino acids, which means there's an extra carbon between the amino group and the carboxylic acid group, so on and so forth. But the ones that are used to make proteins are called alpha amino acids. And most of the biologically relevant amino acids are alpha amino acids. We'll talk about some of the examples or exceptions to that rule, or those that aren't, like for example a beta amino acid later on in next semester. They have some specialized roles. Okay, so once again, Zwitter ion means it's just both positively and negatively charged. This is a fancy name. So these are just different ways of showing the exact same thing. So we have it in the perspective drawing, we have it in the ball and stick, and we also have it in the space filling. If you think back to both Gen Chem and organic chemistry, amino acids are chiral. So the only exception, which is important, is glycine. And the reason why the glycine is not chiral, what does it mean, first of all, that if something is chiral? The carbon, yeah, it's easy when you think about it. The carbon has 4 different things on it. So the reason why glycine is achiral is because its R group is a hydrogen, so it's got 2 hydrogens. But another way to think about it, your hands are chiral in the sense that your right hand and your left hand, they're mirror images and they're non-superimposable. Unless your parents are first cousins or something, then maybe. But no. Like I said, I've told this before, but one time I had a student that did that, and she's like, oh my gosh! But it's because she didn't put them on top of him. And so it was just really funny, because she said it out loud in class. It's like one of those moments I'm sure she wished she could take back. But, yes, so once again, we have both, we can have both that are considered left-handed versus right-handed. The vast majority, if you think back to, I don't know that I covered this in organic chemistry. In organic chemistry, we did plus and minus in R and S, but in biochemistry, a lot of times, we still do R and S, but one carryover from biology comes at DL. And the D and the L stands for dextrorotary and levorotary. Dextrorotary means that it rotates rotates light to the right. It's a mouthful. Whereas levorotary means it rotates plane polarized light to the left. Okay, the vast majority of those that are used in proteins are L. Okay, where are we going? Okay, and the way that we get their formulas from it all has to do from glyceraldehyde. And glyceraldehyde is one that you're going to know by the end of next semester. I didn't have you memorize its name, I don't believe, in organic chemistry. I think we talk about all the time over and over and over again. But by end of next semester, you're going to have glyceraldehyde structure. But glyceraldehyde is the simplest of the sugars. It's 3 carbon containing groups. Glycerol is just 3 carbons where each carbon has an alcohol. So in organic chemistry, we would have called it 1,2,3 propane triol. But biochemistry, the common name is glycerol. So you turn one of those alcohols into an aldehyde, it becomes glyceraldehyde. If you turn it into a carboxylic acid, it becomes glyceric acid or glycerate. And so, but no, the sugar, so then the names get their derivation based off of the fact that they look an awful lot like glyceraldehyde when you line them up. And so that's where it just comes from with respect to the Fisher diagram.
Did you say it was the most simple or most common?
Most simple, because it contains three carbons. And so even when we do the sugar chapter, which I think is chapter 7 of the semester, but it's later in the semester when we do sugars, I don't have you memorize all of the sugars. Glycerol is probably one that you'll know just because from writing it so often, but I don't have you memorize all of them. I have you memorize their classes, but not their actual names. I had to memorize all the way through the first 7 carbon. I mean, it was a pain, and it's completely worthless because you just look it up. So I don't want you to have to do that. That's where, because there's 50 of them or whatever, and so we had as many sayings as we possibly could, and I don't even remember them now, but they were just ridiculous. Like I said, the exception possibly being glycerol, because you just can see it over and over and over again, and it's the easiest one to do because it's just 3 carbons, and each carbon has an alcohol hanging off of it, so it's glycerol. Okay, so we're going to start with the 20 protein amino acids. You can break them down into different categories. There are a couple of amino acids that can follow in more than one category. So, for example, tyrosine, which we haven't got, it's not up here yet. It can fall under one that's considered aromatic. Okay, so whenever we talk about in fact, this one I don't think separates out the aromatics. But when we talk about the aromatic, remember an aromatic compound from organic chemistry, those are things that are based off of benzene and things like that. And they had that special Huckel rule to where the number of pi electrons, and they had to be cyclic and all that kind of stuff. But there are a handful. Phenylalanine, tyrosine, tryptophan, and histidine are all aromatic. But tyrosine is also an acid, and tyrosine is also polar. And so that's why you could have them put into multiple categories. Some of them sometimes. There are some that are just only in one category. For example, glycine and alanine, both of them, which I'll show you in just a moment, those are just non-polar amino acids. They're very plain, simple. They're very important, but they're very plain, very simple. Sometimes the non-polar ones are also called aliphatic, which was a term that we used a little bit in organic chemistry. I just didn't say it a whole lot, but your book, if you read an organic chemistry book, would have used it. It's aliphatic. Those are just non-polar compounds that are hydrocarbons, that are not aromatic, typically. Okay, so once again, phenylalanine, which is a benzene ring, and tryptophan wouldn't fall under aliphatic, they would fall under aromatic. Okay, so I like to draw, just a second. I don't really like the way that they're just showing the R groups. I don't really like the way that they have it drawn out right here. Okay, so what I'm going to do here instead, except, I was going to blank it out for both of them, because I'm not going to remember all the ones that are on that form, and I didn't bring the handout. But I'm going to at least start off with some of them. So once again, this is the backbone. So there's the carboxylic acid. That's supposed to be negatively charged. There it is. Here's the nitrogen. And under biological pH, the vast majority of these will look like this. Then we have the hydrogen that in this would be going away from us up there. And then we have, we have the R group. Now I'm just going to start drawing out the R groups. Okay? And like I said, since I don't have my notes in front of me, there's a good chance that I go out of order or skip one or two, and I'll come back and look at the slide in a moment. So this is the simplest. The simplest of the amino acids is glycine. Good old glycine. Glycine has a 3-letter code of GLY. Please note, when you're doing that 3-letter code, you give the first letters as capitalized, the next 2 letters must be lowercase. It's very important. That way you can tell the 3-letter code versus the 1-letter code. The 1-letter code must be capitalized. Right? And so glycine, even if you didn't look, what would you guess its 1-letter code to be? G. And so it makes sense. And its R group, so I'm just going to draw the R group. So if this was the C, its R group is only a hydrogen. Okay, and I don't want to have to redraw the amino acid backbone every single time, but it's just a hydrogen that's hanging off that C alpha. So what do you suppose what's one aspect of glycine versus any of the other amino acids? If you know that that one has an R group of just a hydrogen, what do you suppose makes it different? Besides it being achiral. So the only one that's achiral. It's completely achiral. What else? What's special in of itself?
I have a question really quick.
Okay.
Is that a carbon and then a nitrogen?
Yes.
Amino group?
Well, yeah, there's just, up in that group one, it's just a nitrogen to a carbon to a carbon.
Okay.
Yeah, there was just a little bit of space. Sorry about that. That's not a... There we go.
Carbon?
That's not, no, this is a carbon here, and then of course the carbon is the carboxylic acid. Now, the carbon that has the R group hanging off of it is directly attached to the nitrogen, because it's the C alpha. So if you remember back to organic chemistry, if we just think back to organic chemistry when we're looking at that backbone, forget the R group, which carbon is going to get top priority? What's going to be the number 1 carbon? And like if you're naming this whatever, which one gets the top priority whenever you're... Yeah, it's the carboxylic acid. It's making 3 oxygen bonds. So that's why that's carbon 1, or the ground zero carbon, you want to think of it. The second carbon is one that's alpha to it. So that's why it's called the C alpha. And this is called an alpha amino acid because the C alpha has a nitrogen on it. Okay, and so that's why, yes, technically when I circled up there is C2.
So if there's the hydrogen on the alpha carbon, would it be fairly easy to react with other?
No. No, not in that sense. No, that was back from whenever you would have, if you had 2 carboxylic acids or 2 ketones or something like that hanging off the same carbon in the middle, then that hydrogen would be a little bit easier to pluck off than what you would think perhaps. But yeah, no, not for here, which is important that it's not, because this is the one that's used for the backbone of all your proteins, and you wouldn't want it to be reactive. So it's inert. But so back to glycine. What do you suppose is special about glycine?
It can share its R group.
It doesn't share it because it's directly attached to a carbon. If this was a person, how would you describe glycine versus, say, something like phenylalanine, which had a big benzene ring and stuff like? It's small. That's why it's so special. So it's the one that gets stuck in, I don't want to say the filler, but anytime that the protein, or many times when the proteins have to make loops and turns and things like that, that's really sharp, you're going to usually see glycine in there. Or glycines also can actually help increase some flexibility of loops and stuff like that because they're tiny, they're not bulky, they're unassuming, but they're very important in that sense. They help with space filling and making those kind of van der Waals contacts, but they don't donate the hydrogen. They can't hydrogen bond or anything because it's directly attached to a carbon, not an oxygen. And so the next simplest one is alanine. And by the way, glycine was spelled, I think it's on that sheet. Come on now, there's like a delay. That's glycine. This is alanine. And alanine's 3-letter code is ALA. Once again, big letter, little letter, little letter. And what do you suppose, even if you didn't have to cheat, what do you suppose the 1-letter code would be? It's an A. And its R group is the next simplest, next to most, well, the next one up in the hierarchy, and it's just a methyl group. And it does many of the same things that glycine does, except it's just bigger. Both of these are not reactive. When I say that, their R chain is not reactive. Their amino end or their carboxylic acid can do various things, but the R group, usually when we're talking about the amino acids themselves, we're referring to their R group. Because all of the amino acids have the same backbone. It's called the backbone. This is the backbone. So almost everything right now is going to be referring to the R group. All right, the next one I'm actually going to draw all the way out, just because if I don't, I'm afraid I'll mess up its R group. So once again, we have, perhaps it's going to come out, a carboxylic acid. We have the nitrogen for the amino group. Come on, there's a 3 there. Then we have this. These are carbons. Once again, this is using that. Okay, so there's a carbon, and then there are 2 methyl groups hanging off of that. I actually like to draw it out this way because it helps me remember which one it is. This is valine. Which is VAL and the letter V. Valine. It's also hydrophobic, so it's an aromatic. So if you think about just if we're going to talk in stereotypes, alanine, glycine, and valine, would these in vivo, do these typically, are they more often on the inside of proteins or on the outside of proteins? They're on the inside because it's a hydrophilic environment. There's lots of water and stuff, so a lot of these help make up the core. Okay, it's called an hydrophobic core, hydrophobic interior, to exclude the water. That doesn't mean that there aren't any on the outside. Many times those that are on the outside may be very important, or it could even be detrimental. So for one example, I forgot the amino acid. I should know this. In hemoglobin, the one that causes sickle cell anemia is a mutation from something to do with valine, and it actually interacts and causes the alpha helices to not be able to go together directly in the correct shape, and so they buckle, and it causes the shape of the sickle cell. Sickle shaped cell, sickle cell anemia. Okay. No, let's go back. All right, and so next we have leucine and isoleucine. So I'm just going to draw the oh, come on now.
Was there anything in particular about valine other than that it's hydrophobic?
No, it's hydrophobic. It's going to be more on the interior. Okay. Oh, I'm not doing a very good job here. Let me just go back. Probably just be able to point it out here and draw it next to it and be. All right. So the only difference between valine and leucine is that leucine has an extra carbon between the little V-looking thing, the little V-looking point. Okay, so remember, valine looked like this when I drew it out. So here's the backbone, and it looked like that. Leucine, if that's the backbone, the C-alpha, it looks like that. Well, obviously, it's not going to be connected to the circle, but... Okay. So it's a CH2 group, then the V. Valine the V is directly attached to the C alpha. If you want to think of it as a V, that's how I remember valine. Leucine has one extra carbon. If you think back, that the carbon's called a methylene carbon, if you think back to organic chemistry. Isoleucine just means it's an isomer of leucine, literally. Okay, and I'm going to draw it down here. Actually, no, I'm not, because it's going to run out of spaces. All right, so that was a valine. Oh, I hate this one. Is so hard just to write on. Okay, remember the letter was V and VAL, which is 3-letter code. Then this one was leucine. That's a U. This didn't come out very well. And its 3-letter code is LEU. Okay, this thing has a vendetta against the letter U. All right. And what do you suppose its 1-letter code is? It's L. Then we have isoleucine. The way that I remembered isoleucine, just because it stuck out with me, is you could remember, if you remember leucine, then just move one of the methyl groups up one. But it just always stuck with me that it's a methyl ethyl, because it just kind of sounds like rhymed. And so isoleucine looks like this. I'm going to go ahead and draw it all the way out as well, so that way you can remember. So we have the carboxylic acid, the nitrogen for the amino group, and then so if that was a valine, directly hanging off that C alpha would be a V. Directly hanging off of the leucine would be a CH2 group, then the V. This one, you have that carbon, the next carbon down, and then I just remembered methyl, ethyl. Okay? Or you could even write it down like a C with a little methyl group and an ethyl group hanging off of it. So it really is the same thing. I shouldn't say that. It really is an isomer of leucine, because leucine had the extra methyl group hanging here, and this is moved up one. Okay. So it's also hydrophobic. Okay. Its name is isoleucine. Okay. What do you suppose its 1-letter code would be? I. Unfortunately, they don't all make as much sense as the ones here, because you can imagine once we start getting to those that have multiple, that start with the same letter, we can't use it. All right, and its 3-letter code is ILE, not ISO. So you just kind of think of it, because the 3-letter code is sort of like it's saying isomer of leucine, ILE.
Is leucine also hydrophobic?
Yes, well, I mean, by definition, what makes something hydrophobic? What kind of functional groups and stuff are going to be hydrophobic? Like, what's an example of a hydrophobic compound here? Nonpolar. So, is this polar or nonpolar? Nonpolar, so it's going to be hydrophobic. Is this one polar or nonpolar? Nonpolar. Remember, we're not talking about this part. We're only talking about the hardware. So it's hydrophobic. That's why these are all aliphatic. We haven't talked about any of the other classes at all yet. There's one other thing that's special about isoleucine. Isoleucine, all of the amino acids have, except for glycine, have one chiral center. Isoleucine has 2. It has its C alpha and it has the C beta. Remember, if this is ground 0 carbon, that's C alpha, that's C beta. And C beta also has a hydrogen, a methyl, an ethyl, and the backbone. So it actually has 2 stereoisomers. So it becomes a little bit more complex than some of the other ones. Leucine doesn't have that because of the fact that all of the carbons are achiral in the R group of leucine. Okay. Then we have methionine, which I'm going to just draw methionine. See, I don't also like the fact that, see, these have little, oh, whoops, I didn't. Go back. Go back, I said. These actually I would count wrong because they use all little letters and you don't usually see that. It should be a capital G, little L-Y. I just wanted to point that out. Methionine is simple. It's M-E-T, so it's met. Come on now. Why is this thing just not wanting to write? Met, and then the capital M. Its R group goes like this. So if this is the backbone, it goes 1 carbon, 2 carbons, a sulfur, and then a methyl group. Okay. And so what kind of functional group is its R group? Is it a thiol? It goes R, S, R. It's a sulfide. Okay. Now, there's one amino acid that I talked about at the beginning that I said you don't have to memorize its structure, at least you won't yet. We're going to find out methionine's got some special uses. What's one thing? Does anyone know? What is one? You should probably already know this. What's one special thing about methionine? It's a what? The first codon. In fact, we're going to find out it's a special type of methionine. It's called formylated methionine, where the backbone gets modified. And so now many times proteins actually end up cutting it off later on when they're post-translationally modified. But the starter codon is always methionine, AUG. Well, that's ATG in DNA, the AUG in RNA. And so it's always, so that's one thing. Another thing methionine is really important for is it's important because it's very difficult. You know, whenever we thought back to organic chemistry, remember it was really hard to add methyl groups to things. Like just to add a methyl group to something was not easy. Usually you had to you would use like free radical halogenation or something like that to turn methane into like chloromethane or whatever, and then you'd have to have a nucleophile come in and smack that and pop the chlorine or the bromine off. Obviously, we can't do that in our body. It's not like we have a bunch of bromine and stuff to go around through there. So methionine is the methyl donor many times. So we have vitamins in our bodies that can utilize methionine, for example, like some of your B vitamins. And it can take that terminal methyl group off. When it does, and it now is a thiol instead of a sulfide, that's homocysteine. You're going to find out homocysteine is also important because it's good because it can take methyl groups off, because there are times that you want to move methyl groups around. And so methionine and homocysteine does that. Also, whenever they get out of whack and you get too much homocysteine versus methionine, it's a key indicator for heart disease. And so, but methionine is just one important thing about it later on, a little factoid either to know for Jeopardy, or, in case you didn't know, I've been on a Jeopardy kick the last couple of days. So, I just started watching it again this week. But a little factoid for Jeopardy is, methionine is used for methyl transfers. It's also the one that's involved with your B vitamin, some of your B vitamins, like cobalamin, things like that. But and it's also your start codon. Okay, but we're going to find out that there are a whole host of things. All right, now the next one. This one's a little tricky. I wanted to draw it out and write it out this way. Okay, it's phenylalanine. Okay, so phenylalanine, and actually this is, even though, because I was a biochemistry major, not an organic chemistry major, and if you remember anything from organic and naming, remember that it was so difficult to remember the difference between a phenyl group and a benzyl group. One was when the benzene group was directly attached. One was when there's a carbon linking it. Well, so coming from a biochemistry background, this is actually how I remembered which one was phenyl, which one was benzyl. Because phenylalanine is alanine. So I'm not going to draw out the entire backbone. But that was alanine. And then what it is that, oh, come on now. No. This iPad and I are not having good. With a benzene on it. So that's how I remember. Phenyl group means it's directly attached. Because it was a benzene that was directly attached to the alanine itself. So that's phenylalanine. Phenylalanine's 3-letter code is really easy to remember. It's PHE. And it's 1-letter code. No, it's F. I know, it's crazy. Because it's a phonetic one. That's because P is proline, which is coming up in just a moment. Okay, so phenylalanine's, it's aromatic. So not only is it nonpolar, but it's aromatic. So it can do different types of bonding than some of the other ones. One thing that we didn't really talk, I don't think, about in organic chemistry that I actually didn't even learn until I was in upper level biochemistries is normally when you think about carbons bonding, things that are hydrophobic, we usually think about them stacking on top of each other. You know, like the fatty acids, like the, let me just draw it out. Maybe it'll let me draw it out. You know, this is what 1, 2, 3, 4, 5, 6. So that's what hexane. And so if you had another hexane come along, they would stack up to kind of maximize their surface area. Does that make sense? So they stack on top of each other, so like laying bricks. Well, aromatics actually, they can do that. So like hamburger patty and hamburger bun kind of idea. But they can also bond in another way. Because, you know, we always draw it with this little donut hole looking thing. That's because if you look down the center of the phenylalanine, it'd be like sort of like looking down the center of a gun. Please don't look down the center of the gun, the rifle of the gun. But there's a hole there. So that lack of electron density, another one can actually come in and bond, make a special kind of bond at a 90-degree angle. To where it's like the hamburger bun or the hamburger patty, or if you think of that being a donut, it'd be like a hamburger getting stuck towards the hole of the donut. Okay, and so it's just another type of interaction that they do that we don't see with other kind of carbon groups. And I'm not an organic chemist to explain like how logically that would make sense, but they just do. And so that's actually important sometimes, the way that they orient themselves inside proteins and biological structures. So that's phenylalanine. This one is probably one of the hardest ones for people to draw and to get correct. Okay, this next one is, phenylalanine was an F. It's tryptophan. So, this is the way I do it. I draw a benzene ring. And then I think about baseball. Because I think this is home plate. I add a double bond. There's a linking carbon. And then it's the backbone. So it's aromatic. So it's a benzene ring with home plate from baseball. Because I know everything that's 5-membered rings for me starts to look like home plate in baseball. But there's nitrogen down below, and since it's aromatic, remember it's got to skip every other bond has to be a double bond. Well, since the benzene ring itself is double, single, double, single, double, single, that means that the other double bond has to be on the far side. But where people sometimes what they forget is it's got a linking carbon between it and the backbone. So you have your C alpha, your C beta, then you've got home plate and benzene ring. And so this is tryptophan. Tryptophan is really important. Does anyone know what's one of the functions of tryptophan besides just working with proteins? Surely you hear about it. I mean,
Is that like hallucination?
Well, not directly. You're close.
Isn't the whole sleep thing a myth?
No, it's definitely not a myth.
Okay, then it makes you sleep.
Yes,
Oh yeah.
because tryptophan and tyrosine for that matter, those are the amino acids that are used, those are the precursor for some of your neurotransmitters, including serotonin, right? And so that's why it feels good. It also helps you, serotonin and some of these that help you fall asleep and do sleep and things like that. So it's one of the reasons why if you eat certain foods that are really heavy in tryptophan, then, you actually get that lackadaisical feel. Okay, and so, but no, it is actually true. That's tryptophan. Without looking or cheating, what would you suppose its 3-letter code be? TRY, and it's not. I can't explain why. It's TRP. I'm sorry. It kind of sounds like trip, but that's not try. It's TRP. And its 1-letter code is W. Okay, and it's because we haven't come to what there is a T, but one way that I remember it's W is on the bottom. It's got a W. Okay, so it's W. Okay, and then this last one that's on this one, on the nonpolar one, is proline. And proline is very, very special, okay? Proline is the only one where the R group, in case you couldn't tell from here, the R group doubles back, and connects to itself. Now, I absolutely hate the way they have this one drawn, because it doesn't even look like an amino acid. So I'm going to redraw it. I'm going to draw it right there. But proline, it makes perfectly logical sense. It's PRO, pro. It's the P for proline, obviously for it's one line code. But in fact, the only way that I can draw it is if I draw out the entire amino acid. And so what I do is I draw out my amino acid. So once again, we're going to start carboxylic acid, C alpha, and nitrogen. Okay, now what you do is, I'm going to use a different color. I'll use red. You go 1 carbon, 2 carbons, 3 carbons, and back to the nitrogen. So because the way they have it drawn there, I don't really like, because you can't really tell it's an amino acid. What it is, it's where there are 3 linking carbons that connect the C alpha back to its nitrogen. Okay. And so now in the amino acid, like if it's inside a protein, of course, then the nitrogen itself would be connected to the next amino acid and so on and so forth and go on. So what do you suppose makes it, this makes it special, but what function or lack of function does it have that is unlike any of the others? If you just think, if you compare it to, it doesn't really matter, I would say compare it to like leucine or valine. Remember valine looked like this, because it's the easiest one to draw the R group. Remember this was the R group. So if you're thinking about valine, what could valine do that proline cannot do? Move. Like it could be like a little propeller, the little flagella. You want to think about it as proline cannot. Proline is stuck. Okay, it's stuck in place. In fact, you have to have a specific protein that we have called racemase that comes in to open it up to change it from the D to the L or the L to the D form. Because otherwise it is stuck in place. It cannot move. So it is many times used to create kinks or turns in your protein. Because it's permanently stuck in place. Okay, so, or if we have like which we'll talk about alpha helices and stuff in the next chapter, you have an alpha helix or something that's going around and all of a sudden it has a kink in it, there's a good chance that that's a proline right there in the middle of it that causes it to kink and get it stuck in one way or the other. So structurally it's very sound. There's no flexibility, little to no flexibility with it, so it's used for structural reasons. And then there's only one other, and we actually talk about this in greater detail later on in the next chapter or two, that proline, for whatever reason, can be modified to where it can be modified where an alcohol gets added to it, added to the little circle. And then that's called a hydroxyproline. And that, almost 1/3 of all amino acids in collagen is a hydroxyproline. And we'll talk about the reason why that's so important. Because if you think about what is collagen, where do you have collagen? Your skin. And what does it do in your skin? The way, it can stretch, it is elastic, but it also, if you just think about it, it's not like an overripe tomato where if you push it, it actually gives it strength, okay? Yes, it can stretch a little bit, it can compress a little bit, but it always comes back to its strength. And that's one of the reasons why it's like almost every third amino acid there is this proline, and so prolines help it keep it very structurally sound. Okay, and so we'll actually even show the pictures for that. Like I said, either later this chapter or the next chapter.